Morning Year 12. So let's have a look at your multiple choice on your high level quantum test. So question 1 asks, which of the following experiments provides evidence for the existence of matter waves? So I don't know if you remember me showing you, I showed you a glass sphere that had a cathode, and this got really hot. Electrons were then emitted because it got so hot, and they were accelerated over a voltage. They then were travelling across the sphere, but what we found was instead of them all reaching this point, we found spheres. Okay, so this was a fluorescent screen, and we saw wherever light was, we knew electrons had been emitted, and so we actually found a diffraction pattern of electrons. Okay, and diffraction is a wave property, so if we've got diffraction, we know we're looking at something acting like a wave, and we know it was electrons that we fired. Okay, so this was the experiment that you needed to remember there. Okay. Question 2. The graph shows the variation with the distance x of the square of the amplitude psi squared of the wave function of a particle. Which graph corresponds to a particle with the largest uncertainty in momentum? So the key here is that you notice this last little bit, the largest uncertainty in momentum. So this is the Heisenberg uncertainty principle. So we're going to write that down. Delta x delta p at most is equal to h over 4 pi. Okay. Now, delta p is the uncertainty in momentum. Okay. So what I can do is I can rearrange this to get delta p by itself and say, okay, well delta p must be equal to h over 4 pi delta x. Okay, so we can see that the uncertainty in momentum, which is what we're looking for, will be largest when this whole thing is largest, which will correspond to my delta x having the smallest possible value. Okay, so we're looking for the smallest uncertainty in position. Okay, that will lead to delta p being the largest possible value. Okay, so remember that these graphs represent the probability on the y-axis of finding an electron at that position. Okay, so if we have a high value on the y-axis for that given x coordinate, that tells us that we have a high probability of finding the electron in that place. Okay, so we can see in A we've got a consistent probability of finding it everywhere. Okay, so this is a very large range of position. It's not going to be this one. Okay, again, we've got multiple places with high probability over a very large range of positions. Okay, and so what we're looking for is the one that has the smallest uncertainty in position. We can see that we have a very high probability of finding the electron in this region round here. Okay, but to the left and to the right of that, we've got a near zero probability of finding the electron there. So that tells us that we have a very small uncertainty in position in comparison to the others, where we can find it across the whole of the x-axis. Okay, so that gives us D. Okay, in 3 then, deviations from Rutherford scattering are detected in experiments. Okay, so this word is crucial in this question. Deviations here means where we see something different. Okay, so if you deviate from the norm, you're different to the norm. Okay, so deviations from Rutherford scattering are detected in experiments carried out at high energies. What can be deduced from these deviations? Okay, so we know in Rutherford scattering what we typically had was alpha particles were sent into gold foil, most went straight through, some deviated from that path and were scattered, and that was because of electrostatic repulsion, because we figured, okay, well, we must have a positive nucleus. The alpha particle is positive, the nucleus is positive, they will repel each other, which causes this force of repulsion. Okay, and so we know that if this is repelling away, this is due to electrostatic repulsion. Now, this was what we typically see in Rutherford scattering. Okay, this is important. The question asks you, okay, well, when we suddenly did this experiment with very, very, very high energy, we saw a deviation from this. This didn't happen. Okay, so that must mean that if we didn't get this deviation due to electrostatic repulsion, there must be another force acting to oppose this at the point where we don't see it happening. Okay, and that's why it proves the existence of a different type of force. Okay, it doesn't get explained by any of the other options. Okay, so question number 4 then. Different metal surfaces are investigated in an experiment on the photoelectric effect. A graph of the variation of the maximum kinetic energy of photoelectrons with the frequency is drawn for each metal. Which statement is correct? So I would highlight maximum kinetic energy and frequency, and I'd think to myself, okay, what equation do I know that links these things? Okay, so I know that the energy of the photon in the photoelectric effect, E equals HF. And I know that if that energy is transferred to an electron, I can say that HF must be equal to the work function of the metal plus the maximum kinetic energy of the electron. Okay, now I know that the graph being plotted is EK max on the Y and frequency on the X. Okay, now let's have a little look at rearranging our equation, and we will hopefully be able to see if we can get to point C. Okay, so we've got EK max must be equal to HF minus psi the work function. Okay, I know then that if this is my Y and this bit is my X, H is a constant, so I now know I have a constant gradient, and plus C is minus my work function. Okay, so what I'm actually going to see is a graph that looks something like this, where I've got minus the work function, and the gradient must equal the Planck constant, and that is a constant value, so therefore they will always have the same slope, which gives me C. Question 5. Pair production by a photon occurs in the presence of a nucleus. For this process, which of momentum and energy are conserved? Okay, let me just sketch you a diagram. Alright, so in pair production we know that a gamma ray produces a positron and an electron. So I've drawn the Feynman diagram for you, and what we can see is that the x-axis effectively represents time and the y-axis represents space. Okay, so position. And so this can be a little bit misleading, because when you look at it, you might assume that it means that the positron is literally moving off in this, but that's not the case, because the x-axis represents time progressing forward, and it's only the y-axis that represents where in space the positron and the electron are. So what this means, hopefully across, the positron has moved up a little bit. Okay, so we can see that the positron moves up, throwing my pen around, sorry, and the electron moves down. Okay, hopefully that will allow you to see, before the pair production occurred, a gamma ray is massless and it's chargeless as well, so therefore there's no momentum beforehand, okay, because there is no mass. But afterwards, the positron moves up and away and the electron moves down and away. And so the sum of the momentum of the two is still 0. So P is still 0 after the pair production has occurred. And so momentum is 0 both before and after. Momentum has been conserved. Okay, now remember that a gamma photon carries energy, E, okay, and that's equal to HF. And we know that the kinetic energy of the positron plus the electron summed must equal that photon energy before and after, which means that energy is also conserved, giving us D. Okay, so an electron of mass m has an uncertainty in position r in question 6. What is the uncertainty of the speed in this electron? So again, it's a Heisenberg uncertainty principle question. So we've got delta x, delta p equals h over 4 pi. Okay, that's the first thing we're going to write down. And now what we're going to do is we're going to replace x and p with the symbols that we are given. Okay, so we know the uncertainty in its position is r. Okay, we know that the uncertainty in the speed is going to be v, so we're going to link momentum to its mass and velocity. Okay, so we're going to write delta r for its uncertainty in its position. Uncertainty in momentum, p, is going to be mv equals h over 4 pi. Now we know it has a mass m, so we don't have any uncertainty in the m, so we can then write delta r delta v equals h over 4 pi. The uncertainty in the momentum must have come from the uncertainty in the speed. Okay, so again what I'm going to do is rearrange this and get delta v equals h over 4 to r m, and hopefully you can see that that gets you to D. Okay, number 7 then. Which of the following observed during a radioactive decay experiment provides evidence for the existence of nuclear energy levels? Okay, so what we see that easily 1 and 3, the spectrum of both alpha and beta, are discrete. Okay, we mentioned that only variables were found for the alpha particles and the gamma rays that were emitted during radioactive decay. So we know that 1 and 3, because they are discrete, it suggests that the energy within the nucleus also is discrete in value. So those two definitely. It's 2 that's a little bit tricky. Okay, so we know that in beta decay, we have the parent, okay, it decays to a daughter plus a beta particle, which is an electron, plus an antineutrino. Okay. We said that to make the model work, we know that the energy of the 3 combined is discrete. Okay. However, for the beta particle itself, which is what the question references, that could take any value within that spectrum, okay, because the energy can be shared between the daughter, the beta particle, and the antineutrino in any combination, okay? And so the spectrum of beta itself, by itself, does not support the model. It only then makes sense when you consider it in relation to the other products of the decay. Okay, so the spectrum of beta is continuous, and therefore it doesn't support the model, okay, which is why you get 1 and 3 only. Okay, question 8. A photon of energy E and wavelength lambda is scattered from an electron initially at rest. What is the energy of the photon and the wavelength when the electron moves away? Let's sketch some diagrams again. Okay, so one crucial thing is to see that the electron was initially at rest, but after the scattering occurred, the electron moved away. Okay, that's important. That means that the electron gained kinetic energy. Okay, so therefore, if this was because of an interaction between a photon and the electron, for the electron to have gained energy, the photon must have lost energy during the scattering. Okay, so lost energy. And so the energy of the photon after the scattering is going some of that to the kinetic energy of the electron. Looking at our E equals hc over lambda, if this E value has got smaller, then the lambda value has to have got bigger because h and c are constant, okay? And so therefore we've got greater than lambda. So we're just using the energy of our must be lower. For the energy to be lower, this whole thing must be lower, so lambda on the bottom of the... Okie dokie. Number 9, a radioactive element has a decay constant lambda expressed in per second. The number of nuclei in this element at T equals 0 is n. What is the expected number of nuclei that will have decayed after 1 second? Okay, so let's write our equation that we get given in our data booklet. N is n naught e to the minus lambda t. Okay, this n in the equation that you're given in the data booklet is how many are undecayed. Okay, so how many of the original radioactive particles are undecayed at time t. Okay, so therefore the number that have decayed, which is what we're after, because it's the expected number of nuclei that will have decayed, must be, so the number that have decayed must be the original number in the sample minus the ones that are undecayed. Okay, that's important. So what I'm going to do is I'm going to say, okay, well, I know that the value that I'm looking for is n naught minus n. And I've got an expression for n. So I can rewrite this. Oops, sorry, it's not very clear. I'm going to rewrite this phrase here and say, well, n naught minus n must be n naught minus all of this, because this is equal to n. Okay, and hopefully you can see I've got some like terms on both bits here. So I'm going to pull n naught out, I'm going to factorise. I'm going to get 1 minus e to the minus lambda t. Okay, this is just from looking at what we have in our data booklet. We're then told in the question that the number of nuclei when t equals 0 is given by the letter n. They've confusingly used the same letter, which is a bit annoying, as a different thing in the original equation. But this n naught is the original number. Okay, so for this particular example, it just becomes n. And hopefully you can see that that gives you answer A. Okay, last but not least then, monochromatic electromagnetic radiation is incident on a metal surface in question 10. The kinetic energy released from the metal, blank. Okay, so if we think about the fact that we have electrons that are trying to escape the surface of their metal, we've got this idea of a potential well. They're trapped within their metal, depending on how bound they are to their atoms. Okay, so if we have a valence electron that's very loosely bound, then all that will require is the work function to escape the metal and whiz off with kinetic energy. But if you have an electron that's trapped within its metal that isn't just a valence electron, it's actually one that's much further in towards the nucleus of the atom, it's tightly bound to its atom, there's going to be extra energy required, okay, in order to free themselves from their atom plus free themselves from the surface. Okay, and so the choice that you need to make is that it varies because the electrons are not equally bound. It depends on what energy level they are in, and that gives you 10, gives you C.